So for example, I'm considering, just wait me a second. Oh, sorry. Okay. So for example, if we consider we have a table here, and then on the table we have an object. So in the previous class, I already introduced you with these objects. The everyday force we meet is firstly, that is the gravitational force, which is the attractive force between the Earth and the objects. Okay, and the second force is the normal force or normal reactions, which is perpendicular to the surface of the contacting surface. Okay, so in fact is perpendicular to the surface. And also we mentioned about the weight. So the weight is the force that the object acts on the supporter. So the supporter of this object is the table. So the weight is the object act on the table in this case. So here the weight is the force not acting on the object but acting on the supporter. In this case is table, and the weight and the normal force obeying the third law of Newton. Okay, so they have the same magnitude, opposite direction, and putting in the different objects between each other, and the magnitude is the same, means you have this. All right, so today we will learn about the friction. So what is it? Okay, so if we consider in this case the objects resting on the table, and the force acting on the objects is that mg and n, and this one is zero because the object is in equilibrium, right? So this is in equilibrium, so the resultant force acting on the objects is zero. Okay, so we have one. Now if I push the object with some force, I push it. For example, I push it with this force, F. This is the applied force. I push it. This means I act on this object is some applied force. Okay, F. Initially, the object is at rest. And we see that the acceleration is zero, so it's still at rest forever, right? So if I apply the F in the object, so what happened? So from the second law of Newton, I will have mg in this case. Okay, is still the same, and now I have additional force is F. And then if you see that if I apply force to the object, but it's very very small, and then what I see is the object still at rest. So the object still at rest means the acceleration is zero, right? It doesn't change the velocity, so this one is zero. Agree? So what do you see in this case? So this guy, these two forces is in the vertical axis. and F is in the horizontal axis. So if you project on O X, Y, on O Y is still this guy is 0, is the same as this. But on O X, this one is 0, but I see now F is not 0. Apply to it, but this 0. So you see, is it okay? Is it okay in this case? The left hand side is not 0 and the right hand side is 0. So what do you think in this case? Raise your hand. Other people raise hand to explain this, except Ngô Trân Hoàng Quân. Ngô Trân Hoàng Quân, or yeah, is very good, but I want to give this chance to another person because Ngô Trân Hoàng Quân is already in my list. David. Still very active. David Duke still very active. Anyone else? Any others?
Could you repeat the question?
So initially with the violet color, the object is at rest, okay? And then if we analyze the force acting on the objects, I have mg plus n is 0 because we don't have acceleration, okay? So now in the blue case, if I apply F on the objects with F is not 0. So according to the second law of Newton, we write it, all the force acting on the object is mg, n, and F. And then the objects in the reality, I still see it is at rest. So it's still at rest means acceleration is 0. So on the right hand side is 0. But on the left hand side, you see, these two guys is 0, but F is not 0, but the left hand side is not 0. And the right hand side is 0. How can you comment to this point? Whether the second law of Newton is not correct, or we should have something else.
Can I?
Yeah, right hand side is MA. I agree. The right hand side. So one person on the chat box told me that this one is MA. I agree. But I mean, it's the object is still at rest. So it means that the acceleration is 0, okay? Because initially it's at rest. Nguyễn Phú. I want to give you mark as much as possible. You can get this mark, okay? I have to see. Okay. Nguyễn Vũ Xuân Minh have just, you have just raised a hand or
Uh,
right?
you ask why this equal to zero, right? I
I
think it's
so actually I don't ask why is zero, but if we analyze all the force acting on the object, we have N, mg, and F, okay? And it's equal to zero. So is it okay, or you have another idea? That is my point. I don't
I
say
think
why.
it's one more force that we haven't mentioned. I think the is I don't know it name. I think it's static fissions, right? Is have the
Yeah. So
must
you
not
mean that
be
you must be the additional force to cancel out this guy, right?
yes.
Okay, very good. So that force I denote is F. So it means that if we count these three forces, we are missing one more force, right?
Yes.
This is not enough. It's not enough because from everyday force, I count, okay, this guy, and this guy equal to zero, and I see, oh, no, but this not zero. So it means that you suggest there should exist one more force, that is F, to
Yes, and
cancel out
equals
this guy.
yeah equals to that force.
Yeah, so it means that F should be equal to minus F, should be, right?
Yes.
So you mean that when this guy appear, suddenly there is this force appear. If there's no this force, is it possible is this force appear?
Uh, I don't think so because we must have a force to push it. So
Very good.
at that time it appear F the F force. Yeah, that's what.
Yeah, right. Okay, very good. Uh, can you give me the ID BI12 and
497.
497? Okay,
Yes.
497. Very good. So thank you. So let me check the chat box. Yes, that means I think there should be friction. Okay. On the right, should have a force with opposite direction. Very good. Quang Vinh. Yes, very good. Okay. So, or you agree with me that if we count the force acting on the objects is this guy, this guy, this guy is not enough. Okay. So we start from the beginning. When there are no applied force, we have these two force is zero, is reasonable, right? But when this guy appear, when this applied force appear, and then if we count three force, and then the object still at rest, it's not correct anymore because the left hand side is not zero. So it means that we have to add one more force appear to cancel out this guy. So they are the same magnitude but opposite direction. And I agree. So this force appear when we have applied force. If not applied force, then it doesn't appear. Do you agree? So now, if I increase the applied force, so the magnitude of this one is increased. I push the object with more force, but still the object doesn't move, right? For example, the object is very heavy. You see, even you increase the pushing and the object doesn't move. But this equation always should be satisfied in order that the left hand side is zero, to be consistent with the right hand side, right? Because the object doesn't move and acceleration is zero. So if I plot a graph for the dependence, of the small f force depend on the applied force. Okay. So I will see that when the applied force is 0, this force is 0. When I increase to this point, for example, then you see this force also increase, right? When this increase, this one also increase in order to cancel out it. So the magnitude of this force changing to balance the applied force. Agree? And now you see in the reality, I still increase the applied force until the object start sliding. Okay? Then I still increase the F until at the point like F apply 0 is equal to F is increased to 0. And then at this point, the object start moving. If start moving means if F greater than F0, then I will have F plus mg plus n plus F apply. So these two guys 0 equal to m a, because it start moving and it starts sliding. Then we have acceleration. And then when it get the acceleration, this force don't increase anymore. So this guy increase, but this guy constant. Not increase, keeps this value. And then this one doesn't change, and this one increase, and the left hand side is a positive, and then on the right hand side is now is positive because you have acceleration. So now it's fine, right? And then from this point to this point, point A, from point O to point A, you just increase the applied force, but still the object is at rest. Okay? During this time, the object is at rest. That we call this force, F here, is friction, but static friction. Static means because it's act when the object is at rest. Okay? It's at rest. The object is still in static, at rest or static. And the properties of the static friction is always opposite to the direction of the applied force. Or the external applied force here is the external force, or sum of all the external force acting on the objects. Opposite direction. Okay? And same magnitude to balance to the external force. And increase the magnitude to balance with the applied force. Okay? Until it gets the maximum value, and then it cannot increase anymore, keep constant. And at this time, we call it a limiting static friction. So at this point, the object start moving. And okay. So the static friction, it appears along the surface, contacting surface between two objects. along this, okay? Along this one, along the surface, parallel to the surface and opposite to the direction with the object tend to move, because it doesn't move, but it wants to move less, it tend to move to the right because the applied force is to the right. So the object want to move to the right. So the static friction here is to opposite to that direction. Is it clear at this point? Okay.
Yes.
So we move to the next one. So what happened when the objects start moving? So in this case, when we still apply the force F prime, but now F prime is very large. Now F prime is greater than the F0 after you. I remind you, we have this graph, 0 here, the friction here, then the applied force here. So it's increase. F0 here. So when F still increase, right? But the static friction doesn't change anymore. So at the value F prime greater than F0, then the objects start moving. And in this case, we still have friction opposite to the direction of the velocity. And then the name is kinetic friction, or some book, they call it a dynamic friction, okay? So the kinetic friction and dynamic friction have, the formula is mu. Kinetic friction is mu. Here is a normal reaction. So the friction is parallel to the surface, opposite to the relative velocity of this object with respect to this surface. So two surfaces, they move relative together. So the velocity of this object with respect to this, so this one is 1 and this 2. So actually F here is minus opposite direction with the velocity of the object 1 with respect to the surface 2, V1 with respect to 2, because the velocity, as we learn together, that the velocity is a relative, have the relative meaning. Is moving with respect to this observer, but cannot be not move with respect to another observer. Depend on the observer, right? Okay. And the magnitude of the kinetic friction is equal to mu multiplied by the normal force. And mu here is called the coefficient of friction. Okay. And is the normal reaction of the surface. So we have this value for the friction. And so it's clear, right? So now, with the friction, we try to do this exercise to understand it. Sorry, in this figure, I have a typo when I denote the objects. This object B Object B is above the object A. B here, A here. So you do this exercise and send me the results in the chat box. Okay? Privately. Anyone else send me the results? Very few people. So actually it's I don't know why, because it's very few people send me the results. It's okay. Nguyễn Minh Hoàng.
Yes.
Wait me a second, I write your name. Nguyễn Minh Hoàng, BI 17172.
Yes.
Can you present?
Yes. So there are I think there are exactly three forces per se that is acting on these blocks. First, there are the tension of the strings.
Okay.
Which is called T.
Okay.
It is
have
moving.
The tension, for example, B is T, and also A, you also have T, yes. And the string is extensible, and yes. Then the tension is, and there are no mass, so the value of the magnitude of the tension is the same everywhere, all the points. Yes. Okay. Yes.
And so there is next, we will display the frictions,
yes.
The force frictions between B and A.
Between B and A, okay.
And there's also the friction between A and C, A and the ground, and I call the ground C, so it's better for me to follow.
All right, so you call the table is object C.
Yes, yes, yes.
All right, so now you consider the friction acting yes. on which object?
The friction acting on A and
okay.
the table.
On object A, okay. So the friction acting on A, but caused by the table C.
Yes.
And which direction?
It will be the opposite direction, or with the same direction with the tension right. of the T.
Yes. So the velocity is here.
Yes, velocity.
So the
energy,
friction should be opposite direction to the
direction.
velocity.
Yes.
Very
Yes.
nice. Very good. So this friction I denote is F CA. Okay.
Yes.
C acting on A and
Yes.
putting at the object A.
Yes.
Idly. Okay.
And now to have a move with a uniform velocity would be, so that means that it will have B and A will have the same speed, but when we pull A forward, B will move in the opposite direction with the same speed, because due to the string be wrapping around the circle thing,
the pulley, and
yes, the pulley.
is inextensible. So
Yes.
the velocity of A and B is the same. I agree.
Yes. And now to have this force, I consider the force of the strings, the tension of the strings will be equal to the frictions of block of the frictions that apply on B. So basically, it's like the P here, the force P that will be moving A will be equal to the frictions, the force that apply, friction force apply on B plus with the force friction apply on A plus with the tension of T, so that the P can move A with the same speed for the uniform velocity. That's what I consider. That's what I think. So because I write a F, I think you should write like an F, B, and A too, so that you can.
I'm sorry. I'm muting. So
Yeah. I don't think I can actually explain it too well. I just know that I just considered the tension to be the same with the frictions between block B and A, which is 10 newtons. So I will add all the force together to equal to P. So.
Okay. So the friction of the object 1 acting on object 2 is the opposite direction with the velocity of object 2 with respect to object 1. Okay. So now we consider A and B. Now you determine the friction that B acting on A. So it's put at A. So you need to consider the velocity of A with respect to B. It's which direction? V, A, B, which direction?
Velocity of A to B, I think will be same direction with P.
Very good, because B, A go to the right and B go to the left.
To the left. Yes,
So
yes,
A with respect to B should be go to the right. VAB.
Yes.
So the friction at surface AB acting on A is
we'll go into the left, yes, because
friction of B acting on A.
Yes.
Do you agree?
Yes, yes.
Okay. So now, similarly, the friction that A act on B is which direction?
The friction of A on B?
Putting at B.
I think will be also the same direction with a velocity VAB, I think.
So you need to determine, right? So the friction of B, of A acting on B, okay?
Yes.
A acting on B, putting at B.
Yes. Oh, yes. It will be the same direction.
Minus.
V minus.
VBA.
Yes. Oh, yes. Oh, yes.
Here is VAB
AB.
and
Yes.
VBA
Yeah.
is this direction, okay?
Yes. Yes. That's true.
So the friction here
We'll point to the right. I think we'll point to the right.
go to, very good. So here is F dot A acting on B. Agree?
Yes.
So this putting at B and this putting at A. And actually these two forces, they are internal force between two objects A and B. For example, if you consider A and B in a system, if you consider a system containing A and B, then the friction between A and B is the internal force. Like A hit B a force, then B will act back A a force, obeying to the third law of Newton. That is why you have A on B equal to minus B on A. Do you agree?
Yes.
Yeah.
I agree. Yes.
So now you apply the second law of Newton for A and B, right?
Yes.
For A. For A, you have how many forces?
We have P.
Very good.
Then we have the friction F.
FCA.
SCA, yes. And also the friction of I think B. Was it
BA.
BA?
Very good. And
also FAB.
why FAB?
No.
AB is acting on B.
Oh yes, AB is acting
And
on B.
I'm considering
On
A.
of A only.
Okay, of A only, right. Anything else?
T. I forgot.
Very good.
I
Tension.
forgot.
Attention, right? And
Yes.
this one equal to actually is MA and the acceleration.
Yes.
But how about this?
So FCA P we don't have to know. Oh, the acceleration.
Acceleration equal to what?
Well, I didn't calculate acceleration.
You can see it from the they give the information.
Oh, it's 0. Okay. It's 0.
Why?
Because it's moving with a uniform velocity.
Very good.
Acceleration. Zero.
Very good. So uniform velocity means the velocity is constant. And velocity constant means acceleration is 0. Very good. And now maybe you choose a coordinate to project this on. I choose the coordinate is OX like this.
Yes.
Oh, okay. So you project on OX of this equation, you get P
minus
very good, CA.
CA minus FBA
Very good.
minus T.
Very good. Equal to 0.
Yes.
I have one equation.
Now
So,
we just move it to the right, all the minus.
Okay, so you get P equal to FCA plus FBA plus T.
Yes.
FCA is
14.
below A at the table. 14.
Yes, 14.
FBA between B and A.
B and A. That will be 10.
10 and tension. 24 plus the tension. And then how can you calculate the tension?
I just consider the tension to be also 10. So
Why? Why the
um,
tension is 10?
I think because if the tension, oh wait, I just think that if the tension is the string is too bigger than the frictions between the block A and block B and A, the string would just pull the block away from the block A, pull block B away from block A. So I think that the force needs to be equal. So for B to balance on A with to move balance on A. That's just my way of thinking.
But the object B is still moving on the object A.
Yes, it's still moving.
So maybe it's better you apply the second law of Newton for object B, okay?
Yeah.
To see what happens. Okay. So the second law of Newton for B.
For B, yes.
How many force? Sorry.
There will be T. Hello?
Wait a bit, she said she's going to do something.
Okay. Oh, she's gone.
Yep.
Okay, sorry. Let's continue.
Yes, there will be T. Oh,
T, right.
Yes, T.
T
FBA.
plus F AB or BA? A acting on B, right?
Yes.
Because you are considering B.
Oh, yes, considering B again.
This one is equal to MB acceleration, right?
Yes.
And equal to?
0 again, I think.
Because
uniform velocity.
Uniform velocity and velocity of object A and B is the same.
The same, yes.
Right. So now you project this equation on OX.
OX.
And
that
then
would
you
be
get
T equals to T minus FAB. T minus
very
FAB
good. Very
equal
good.
to 0.
Okay. So then
T will be
equal
equal to FAB.
Equal to?
FAB will equal to 10.
Okay.
Newton, yes.
Right. So this one is 24 plus
Plus
10. And the result is 34 Newton. Very good. So many people send me these results only. Maybe you forget the tension. Is it clear? Thank you very much.
Yes.
Minh Hoàng. Very nice. Any questions?
No questions.
You have.
No question.
Okay, no question. Right. So I clear this. Sorry. Yes. Okay, so I see Hoàng Nhị Hà want to some, yeah, okay. Yes, yeah, doesn't have the electricity. Okay, right. So, oh. Maybe she's left. Okay. Sorry. So we move to this one. So if in this case, okay, we try one more, this side. So remember that during the times I call one person to do the exercise, if you have questions or comments, I still take into account. So pay attention during the classmate present the solution, and then you can ask a question or give some comments. So I will take into account. It's very, very good action. Okay. So that we have more people to be on my list, that I can give you the bonus mark for the final results. Sorry, this exercise, we take the gravitational acceleration 9.81 meter per second square. Okay. Oh, okay, so why is many people send me the results?
I'm still trying to figure out the answer, so that's why I didn't answer yet.
Okay. Wow. Uh-huh. Mm-hmm. Okay, so I call one person to do this one. Nguyễn Nhật Minh. Can you hear me?
Yes.
Nguyễn Nhật Minh, can you present the results?
Oh, I think I can. So first we
BI 12286. Okay.
yes. Okay. So first we can analyze the forces on the block.
Very good.
Well, there's
Analyze the force
P.
acting on the block. Okay. P.
The first one is P, perpendicular to the ground. And
so P is vertically downward.
yes.
Okay. Good. And
The second one is the normal force.
normal force of the surface, which the direction is
Perpendicular to the surface
inclined.
of the plane.
Very good. So it's perpendicular to the incline, right?
And the final force is friction.
Friction.
Yes. Since the block is moving downward, so the friction should be on the upward.
Very good. And
Okay,
along the
so
surface, right?
yes. And from here, P, I analyze into the two smaller one.
Very good.
One,
So you
the first one
analyze.
is P1.
You
yes,
analyze or
direction.
you resolve EP in P1 and P2, right?
Yes.
What do you mean is you analyze this one or resolve P1 plus P2 perpendicular to each other?
Yes.
Using time this. Okay.
You can easily see that P1 is equal to mg psi 30.
Okay, so alpha. So P1 is P sine alpha. P2 when alpha is 30 degree. P2 is
P cosine alpha.
P cos alpha. Very good.
We use the Newton's second law. We have
Newton's
the
second law.
equation. P1 plus P2 is all the force together.
All the force
equal
together.
to MA. Yes.
This one is P, right? Plus F plus N. All the force equal to
Equal
FA.
to MA.
Very good.
We choose the OX. Along the surface of the plane.
Yeah.
With the direction downward.
Okay. So he chose OX like this. Maybe OY like this. Okay. It's okay. So
yes,
we project
on
OX. Project
on
one
OX.
on OX. You get
We have P1 minus F equal
friction.
to MA.
Very good.
We need to calculate the F. Yeah. F equal to P1 minus MA.
P1 minus MA.
Yes,
And
the
how-
distance that the block travel is 2 meter and
1
can be
meter.
calculated with the
1 meter
yeah,
in
1
2
meter,
seconds.
1 meter.
So
Can
you use the
calculate like
formula.
S equal to 1 second
1/2,
80 square.
not 1
1/2.
second.
Yes.
1 second is okay.
80
1 second is okay. Sorry. 1 second is
80
also
square.
fine. 80 square.
Yes.
All
If
right.
replace S with 1 meter and T is 2 seconds, we have A
Yes.
equal to 1/2.
2st square is 2 minus 1 divided by 2 square is 1/2 second square. So
Yes.
P1 is
F
P,
T
right?
side.
For
Yes.
G sine 30 is 1/2, right?
Yes.
Minus
Minus 4 and minus 4 multiplied by 1/2.
minus 4 multiplied by 1/2. And the result is
17.62 meter.
very good. It's a good result. Thank you very much, Nhật Minh. Any question? Anyone is not clear at this point? This exercise?
Teacher,
Yes.
I don't know why, but if I use the other two equations to calculate the acceleration, it just doesn't appear to be 0.5. Could you show me where did I do wrong?
Okay. Okay, no problem. So let me clear this table and then I answer the question. Everyone is okay? Everyone
Yep.
is okay?
Yep.
Okay. Right. So Đức Long, can you present and then I will see where you are wrong, right?
Okay, so
Tell me.
it's about the acceleration part that I did wrong. So
Yes.
I used the equation V equals to V0 plus AT
V
equals
at the
to,
time T.
yes, equal to,
V0 plus AT. Okay,
yes.
good.
And then I just plug the number in, which is like 1/2, like 0.5 equal to 0 plus AT.
One is where?
It's 1 meters over 2 seconds to calculate the velocity.
So you calculate Vt equal to 1 divided by 2?
Yes.
So this correct, this not correct. Equal to S divided by times?
Yes.
This not correct, okay? Do you know
Okay,
why?
Yes.
This S divided by times is the average average velocity. For example, from point A to point B, and the distance is 1 meter. So velocity, average velocity AB equal to SAB divided by time interval. So here is the average velocity. And velocity at the time t is the instantaneous velocity. So the velocity at B equal to velocity at A plus AT. So in this formula is a velocity at B. But in this formula is the average velocity when you travel from here to here. That is a difference, okay? And you can prove this guy in this in the constant acceleration is 1/2 VA plus VB. You can prove this formula. It's okay? This
It's okay, thank you.
Okay. That is a difference. All right. Okay. So it's better in this case, you apply the distance is 1/2 AT square. It's correct. But it's very good to ask the question if you are not clear at any point. Sorry, I take the charge to my computer. 1 second. Okay, sorry, I have to take the charge to my computer. So we continue for the next part. So far, we learned about the friction, right? So now I continue to introduce another force, that is obey the Hooke's law. And this force is called elastic force. So in this case, imagine that we have a spring, a coil spring like this. And for example, it's a natural length is like this. This is a natural length. And then we move it to the left and make the spring extend an extension delta L equal to L minus L0. So in the moment, just forget the direction. We just care the magnitude value. Okay, L is the length of the spring at the new, L is new position, and here is the natural length. Okay, so when we make the length of the spring is longer than the natural length, so then we call it is a positive, right? L greater than L0 is a positive. And now the direction of delta L is go to the left. Okay, because you make the extension go to the left. And in this case, you call it an extension. Another case, for example, I take another case. The object is here, somehow is here. And then still you fix here, and then now the spring is here. And the length of the new here is L. And if I calculate delta L is equal to L minus L0 is negative. And this we call it compression. Compression. And now delta L having the direction go to the right. So in this, we have this, the second case, and this violet color, we have the first case. So in the first case, when we move the object to the left, comparing to the original one is here, the spring is extended, and there will be a force of the spring acting on the objects, having the direction opposite to the extension direction. direction of extension is to the left, and this force go to the right. Okay. And another case, when in the compression case, you say that when you make the spring is shorter, you feel in your hand there are some force pushing you, pushing the object. In this case, it's pull, right? Violet color is pull, but with the green one, it's push. And then the force of the spring acting on the object is here, F. So it's the opposite direction to the direction of the expansion. It's a go to the right. It's a delta L. So the force is a go to the left. Conclusions. If you have a force between the spring, is an elastic force acting on the objects, making the spring extended or extending with this case or compressed. This force is equal to minus K delta L. Minus sign here is vector, minus sign here, implying that this force is always in opposite direction to the direction of extension. The extension goes to the left, the force goes to the right, vice versa. The extension goes to the right, the force goes to the left, always opposite. And the magnitude F is K multiplied by delta L, absolute value, if you take the magnitude. And K here is a constant. K is a constant for different coil spring. So each coil spring, you have a value of this constant. Okay? And given a coil spring, K is constant. Is it clear? And L here is, you can call the actual length, and L0 is the natural length. And this is the Hooke's law. This is the Hooke's law. And the Hooke's law, it has a lot of application in the reality. And you see that, so from the Hooke's law, we can have a way to quantify some force acting on the object, or how to weight the object, right? To measure the gravitational force acting on the object, which you do every day. So how can we do it? So for each spring, I have this spring. Having the natural length, I load by a mass m0, such as the gravitational force acting on this is m0g, and then the elastic of the spring acting on the object is here, F0. If I take it a sample object in the laboratory, so you know that in the
Professor, your mic is muted. We can't hear you.
so you can hear me?
Okay, now it's okay. Thank you.
Okay, sorry. Thank you. So we make some sample object with having before the weight. For example, you have a weight here is 1 Newton. Okay. So the mass here is in equilibrium. So you have F0 equal to m0g equal to 1 Newton. You know already. And this one obeys the Hooke's law. So you have then delta L0. So then you measure the extension of this spring. You measure it to see the extension. Okay. And now you apply with with different force. You load with another line with you don't know the value, not mg. So in this case, F equal to mg, which we want to measure. We don't know, right? We don't know how is the weight of this mass. But we know that it's still in the elastic limit. So it should be obey the Hooke's law. And then its extension is delta L. So the natural length is here, and the extension delta L0 is here. And with the new load, you get the extension is delta L. No, delta L. Delta L, okay? Delta L. Delta L0 is here. So we have this equation. So from here, I divide side by side. I get F by F0 equal to K here is the same. So delta L by delta L0. Delta L0 is known already. So from here, F will be equal to delta L divided by delta L0 multiplied by F0. So we see that delta L0 you know already. And then you can measure delta L to see how much delta L bigger than delta L0. For example, this guy is alpha. So you have F equal to alpha F0. F0 if is 1 Newton, you know already the sample. So then alpha giving you the value of F, okay? For example, at this point, you can measure the extension of L0 is 1 centimeter. And then in this case, you can measure delta L is 5 centimeter. So this means that you already load here a force equal to 5 Newton. So this have you a way to quantify the force. And this in the normal life, you use this to weight the objects, how many kilo, right? Because this is they already know the scales on the line is 1 centimeter corresponding to some sample, and then you just make depending on the extension, you can measure how many times your new extension greater than the sample 1, and this value is alpha, give you the value of the force you want to measure, or the force acting on the spring. Is it clear? So it's very helpful, this. So conclusions, elastic force is K delta L, where delta L is actual length minus natural length. K delta L is a magnitude, and the direction is always opposite to the direction of extension. Okay, clear? And in this point, we define the value, the quantity called the strain. Strain is what? Strain S equal to delta L divided by L0. Give you the extension of the spring in each unit of length. For example, in 1 meter of the spring, you have the extension equal to S. So the extension for each you need a blank. Okay, that is a string by concept. Any question? Sorry. Okay. So we stop for the Hooke's law. So the everyday force, you know, is a gravitational force, normal force, weight, Hooke's law, elastic force, and friction. Okay, which you meet every day in the life. So now we move to the next chapter. Chapter 2 is about the part is still chapter 2, collision part. So what is the collisions? So the collision, for example, if we consider two objects, M1 and M2, they collide each other. And then we consider the collision in the case satisfies these four conditions. So the collision is a phenomenon which has this feature. Firstly, it occurs in a short time interval. So M1 collide to M2, and then after collision, they go far away together. So before the collisions, M1 moving with the velocity U1, M2 moving with the velocity U2, and then they collide. For example, this guy move faster than this guy and go and hit this. They collide. And after collisions, they change the velocity. And the velocity of M1 is V1 and M2 is V2. Okay? So the time to happen here during the collision here, taking very fast in a short time interval. And the second property is what happens after collision differs from what happened before collision. So after collision, the velocity of two objects changes. This guy, you see, it changes. If it doesn't change at all, we don't see it collide. Okay, so two persons go together on the road. Person A, person B, and person A said that, oh, guy, you are hitting me or you are colliding me. There's some accident, right? But this guy said that, no, nothing changed. The velocity still doesn't change before and after collision. So I don't collide you, right? So if we consider there's a collision, so there something should be different before and after the collision. That is one condition to should be satisfied. Okay. And the third property is colliding bodies may be assumed to be constitute a closed system. So these two objects is a close, making a closed system. Means if you consider the system containing M1 and M2, then there is not any external force acting on these two objects, or the external force acting on these two objects balance. Then we call this system is closed system. For example, in this case, we should neglect the friction. Okay? Neglect the friction. Between, for example, we have a table or a rod. Just before collision and just after collision, you don't have the friction here. Otherwise, these two objects are not a closed system. Okay. And remember that if they are in the closed system, we have the momentum and energy is conserved during the collisions. So what does it mean? Momentums. Firstly, momentum of the system is conserved. Means before collisions. So do you know the momentum is of objects is a product of the mass and the velocity. That is the momentum of object. So now you consider a system containing M1 and M2. So you can calculate the total momentum of two objects before collisions, initial, equal to M1 U1 plus M2 U2. And total momentum of the system after collision. After collision. Final should be equal to M1 V1 plus M2 V2. And then the momentum of the system is conserved because the system is making a closed system. There are not any external force acting on the system. So the total momentum of the system is conserved. Then you have M1 V1 plus M2 V2. Agree? So here, telling you the momentum conservation of the system. And remember that here you have the vector sum. This is a vector. It's not the sum over the magnitude, but over the vector. Okay? Vector sum of linear momentum. So this guy is called the linear momentum. After collision, equal to vector sum of the linear momentum before collisions. Okay? All right, so here I give you some definitions. And then if this happens, we say that the linear momentum is conserved. It's conservation. Sorry, his chapter 2, I have a typo. All right. So now, if I consider chapter 2, M1 and M2 collide. And before the collisions, the velocity of M1 is denoted as VI1. VI stand for initial, 1, vector. And VI2, initial, vector for object 2, velocity for object 1. This is the velocity of M1 after collisions, VF1, and this guy is a VF2 after collisions, okay? And then we assume M1 and M2 collide in one dimension. One dimension means they are on the straight line. They are on the straight line to be simple first, okay? We are considering one-dimensional collisions. The second point is we ignore the zero net external force in the direction of moving. So the total of external force acting on the system M1 and M2 is 0. This means that, okay? So M1 acting on M2 and M2 act back to M1, but these two forces is an internal force. You should distinguish between internal force, external force, external force. Internal force, for example, you are considering M1 and M2, internal force is the force acting between them during the collision. external force is the force of another object outside the system, acting on the system. Okay. So in this case, the external force, you neglect the friction. You only have gravitational force of the Earth attracting, but the gravitational force is a balance to the normal force. So totally is 0. So the collision should happen in the horizontal surface, so that gravitational force balance to the normal force. Otherwise, you cannot apply the momentum conservation. So if these two conditions satisfy, then the momentum conservation give you vector sum of m1 vi1 plus m2 vi2 vector equal to m1 v1f v2f, okay, f2 f1, okay. So the final velocity is the initial velocity, and multiplied by the mass, you have the initial momentums equal to final momentums of the system. And in one dimension, because it's one dimension, so you can project along a x, you get this projection value. And here I denote is a positive. Here means the velocity here can be positive or negative. For example, vi1. If I wrote here, it can be positive if it's pointing the same direction as OX. If it's negative, same OX. Negative is if opposite, right? To OX. If it's opposite to the direction of OX, then the value of the velocity is negative. So if you don't know any the direction of it, you can write in the projection value is plus everywhere. In this case, if you solve down the value is positive, you say that the direction of the velocity is the same direction as OX and vice versa. If it's negative, you get the opposite direction of velocity or with respect to the OX, okay? So now, so for every type of collision satisfy these two conditions, you can apply the conservation law for the momentums of the system. Okay? And now, how about the energy is conserved or not? Then we distinguish in 3 cases. We distinguish in 3 types of collisions. So first type of collision is called elastic collisions. So in the elastic collisions, you have total kinetic energy of 2 colliding objects is conserved. Okay? So this means that kinetic energy of an object is 1/2 mass square v. Okay? So you consider the system containing M1 and M2. So the kinetic initially of the system containing 2 objects, the kinetic of M1 v I1 square plus 1/2 M2 vi2 square. So on the left hand side is the initial kinetic energy of the system. Similarly, on the right hand side, you have the final kinetic energy of the system. If Ki equal to Kf, you call this type of collisions is elastic collision. Okay? The second case If this not satisfied, then we call it is inelastic collisions. Inelastic collisions means now you have Ki not equal to Kf. And in fact, initially Ki is greater than Kf. And then implying that we have some energy or kinetic energy equal to Ki minus Kf already transferred to another form of the energy. And usually that is the heat on the surface or the heat between two objects. When they collide, the surface of the object is hotter. And there are some fraction of the kinetic energy of the initial object system already moved to another type of energy. And in this case, the kinetic energy is not conserved anymore. And the collision we call it an inelastic collision. Okay? Cool. And in the inelastic collisions, we can, there are some particular case that after collision, two objects stick together. Two objects stick together and moving with the same velocity. So in this case, we call it is a totally inelastic collision. The special case of this case is a totally inelastic collision. Means that two objects stick together after collision and they moving with the same velocity. Okay, so can you distinguish a different type of collisions? So I repeat, for three cases of the type of collisions, you can always apply the conservation of the momentums. Conservation of momentum because momentum is a vector quantity. So when you apply the conservation law with the momentum, you need to make a vector sum. It's not the, it's vector sum, remember, not the magnitude sum. That's the first point. And how about the kinetic energy? Kinetic energy not all the way conserved during the collision. It can be conserved for some case, but not the other case. So they distinguish in elastic collision and inelastic collisions. So elastic collisions, you have conservation of kinetic energy, and in elastic collision, you have you are not allowed to apply the kinetic energy conservation. And in this case, there are some fraction of the kinetic energy already converted into other form of the energy. Okay. So disturb me if you have any question. Otherwise, we move to the next part. So you have these three types of collisions. And then if you use another definition that is called Newton's law of restitution, E. So you can distinguish, or you can distinguish type of collision using the conservation of the kinetic energy as we have known, or you can make another definitions that is based on the restitution. Newton restitution denote is E. So what is E? You take the relative velocity after collisions. After collision is V F1 minus V F2. It's a relative velocity, relative equal to minus E of multiplied by VI1 U. Okay, V minus VI2. Relative velocity before collision. Relative velocity after collision equal to minus E. Okay. So in this case, if you use this definition, then if E equal to 1, you have elastic collision. E equal to 1 means the magnitude of the relative velocity before and after collision doesn't change. And in the case of the inelastic collisions, you have the value of E for between 0 and 1. And for the total inelastic collision, you have E equal to 0. So if equal to 0 is 0, and then you have VF1 equal to VF2, they stick together and moving with the same velocity, you have E equal to 1. Okay, so conclusion. In general, we have these three types of collisions. It can be distinguished using kinetic energy conservation or using Newton's restitution E value. Okay. All right. So now I'm trying to introduce in some case, for example, in the case of elastic collisions, how can we apply the momentum conservation law and kinetic energy to solve the SSI? Okay. So in case you have in case you have the elastic collision, so object 1, object 2, before the collisions, it has the velocity u1, u2, and after collisions, they are moving with a different velocity. This guy is a velocity v1, and this guy with velocity v2. Okay, any. And given that the collision is elastic. So with the elastic collision, you can apply first momentum conservation. Total momentums before, after collision equal to total momentum before collision. And remember that here I make the plus and I don't know the direction of the velocity. So V or U can be positive or negative. I have OX. Is a positive if they are pointing, moving with the same direction as OX. Negative is opposite direction. But here is a one dimension. One dimension, okay? And then applying the momentum conservation, I can write this equation. Is it okay? So now I apply, V1 not equal to V1 minus V2. So V1 minus V2 equal to minus E, U1 minus U2. So at this point, you can use Newton restitution E, or you can use the kinetic energy conservation. They are the same. So now, for example, you can this equation and apply E equal to 1. E equal to 1, then you have V1 minus V2 equal to minus U1 minus U2. So you have the second equation. You have second equation. And from this second equation, given that this one is known, before collision is known, then now you are trying to find the final velocity of two objects after the collision. Then from 1 and 2, you solve V1 equal to this, V2 equal to this. So please check at home, okay? Check this at home. Okay. So you have this value. And obviously, if you know the condition of the collisions, you apply this rule, and then you can know the velocity of two objects after collision. Okay, and here is the in general case. Okay, so we check this formula at home. All right, so we go next. Next slide. Oh. Okay. So from the previous slide, I repeat here, we calculate the velocity of two objects after the collisions. Now we are considering three particular cases which happen in the reality for you to see more clear. So for example, and remember that here is an elastic collision, okay? The first case, if you have two mass is the same, M1 equal to M2. Okay, the same mass. What happened? M1 equal to M2. So the first case, this guy 0, this guy 0, and you have V1 equal to U2 and V2 equal to U1. You see, the first object, the second object, initially velocity U1, U2. And then here you see V1 equal to U2 and V2 equal to U1. So it's somehow these two objects, they exchange the velocity before and after collisions. Okay? For example, if initially this guy is at rest, for example, U2 equal to 0 and U1 is not 0, go here to hit this guy. And after collision, V1 equal to U2, so V1 is at rest. And V2 is moving with this velocity, so it's moving. Okay, so you have a toy. You have a toy, Via, or it's a name like this. So all the object is the same mass. So when this guy go to hit this guy is at rest, and this guy is moving to hit this one. And after collision, this guy stop and this guy move. So it's collide and this guy move and this standing. Okay, so this is you see in the reality from the top. Okay, the second case, I take the different color. In the second case, when M2 much bigger than M1 and M2 is at rest. So you imagine this case is you have a wall. The wall is object 2. Okay? Well, the wall is fixed. So the mass is a very big mass. And object 1 is you imagine there a ball. going to hit the wall. The wall is at rest. U2 is 0. Okay, so in this case, what we have from what we obtain from this general formula. So we try to calculate the velocity of the ball after it hit the wall. So you can guess the results. Okay, the result is what? The ball hit the wall and the ball is back and the wall is still at rest. Agree? The ball is hitting the wall and it's turned back and the wall is still stable. So now we see whether this equation work or not. Okay. So in this case, M2 is at rest, so you have U2 is 0. So now I calculate V1. Alors, U2 0, so you don't have this term. So it's just M1 plus minus M2 U1 divided by M1 plus M2 because M2 much bigger than M1. So I divide by M2. So we have M1 by M2 minus 1 U1 divided by M1 divided by M2 plus 1. Okay. So because this condition, what does it mean, this condition? This means that if you take M1 divided by M2, this get to 0 because this is very large and this is very small. So this 0, this 0. So the result is V1 equal to minus U1. The ball go this direction. After collision is minus sign. Go back with the same velocity, same magnitude, but opposite direction. So it's okay, right? It works. It's okay. And how about V2? V2, okay, you don't have this one. You have this. V2 is 2 M1 divided by M2. So you take M1 divided by M2, U1, divided by 1 plus M1 divided by M2. So this one 0, this one 0, so this 0. So V2 is 0. So the wall still at rest. So it's in this case, you see that these two formulas still working very well. Okay. So you consider the third case. The third case, you consider M1 is a very, very large comparison to M2. And M2 is at rest. Oh, what in the reality? What is the case? So you have very small guy is standing here, some bicycle, okay, or some object is standing at rest. Very small. U2 0. M1 is a very big guy. There's a van or it's very big car with M1. The third case, I take another color. Alors, this color. M1, M2, very small and initially at rest. And this guy moving with the velocity E1 and hit the small guy. So we see what happened, okay? This is actually the accident on the road. If you see a very big van hitting some very small car, and you can imagine what happened. So initially this guy at rest, and this guy go from behind and hit this guy. And we see after collision what happened, okay? So to see it, we apply this formula. So in this case, U2 is 0. U2 0, so you try to calculate V1 in this case. V1 in this case, you don't have this term. You only have this term. M1 minus M2 divided by M1 plus M2 U1. Okay? Next. Because M1 very large comparing to M2, so it means that M2 divided by M1 go to 0. So I divide all this by M1, okay? Then I get 1 minus M2 divided by M1 over 2, 1 plus M2 U1. So this one 0, this one 0. So this one equal to U1. So V1 equal to U1. So this guy initially at rest. When this one hit it, it gained the velocity is the same as this one. V1 equal to U1. Moving. And how about the big guy after collision? We calculate the velocity of the big guy after the collision, okay? So the big guy have the velocity after collision is V2. So in this case, U2 is 0, so you don't have this term. So V2 is this guy. V2, I don't have space, I try here. M1 and I divide to M1. So it's 2 U1 divided by 1 plus M2 by M1. This is 0. So this is 2 U1. I'm sorry. V2 is the velocity. This the small guy is the number 2. This is the number 1. So V2 get the double velocity of the initially this guy. So is this moving after collision moving with the 2 U1, and the big guy having this velocity V1 still the same. So the velocity of the big guy after collision doesn't change at all. So it means that it's too heavy. So it feels nothing after collision, right? Nothing changed for this big guy. It's go to hit this and it doesn't affect anything because it's too big. It doesn't feel anything, any change. But the small guy initially at rest, but now it gained the velocity twice of this velocity. So you assuming that a very small guy standing on the road and the very big van moving with the velocity, you imagine, for example, 100 kilometers per hour. After collision, this guy moved with the velocity 200 kilometers per hour. Can you imagine that? Initially at rest and push, go away very fast and disappear. It's very dangerous. And the big guy here doesn't change at all. Nothing happened to this one. So you see, in the reality, it's a very, very dangerous. If you go, it's very small by motorbike or very small car or a bike. There is some accident happens. So it's very dangerous. So you should be careful. Okay? In this case. Is it clear? Okay, so I just make some example for you and also make some application in the reality so that you can feel the applications of the collision condition so that you can estimate the condition before and after collision, what happened, right? So that is the physics. You can change, you explain the reality happen every day in the normal life. So in case of the totally inelastic collisions, you can apply the final velocity is the same. And then in this case, if you apply the momentum conservation, you get this one. And then you can calculate the final velocity is equal to m1 v1 plus m2 v2. So this one is nothing but center of mass, velocity of the center of mass. So you have two guys, m1, m2, and between them there is the center of mass, something here. The center of mass of these two objects is defined by the velocity of the center of mass equal to m1 v1 plus m2 v2 divided by total mass of the system, the center of mass velocity. So after collision, velocity of two objects equal to the velocity of the center of mass before collision. Okay. If initially v2 is 0, and then you can calculate vf is as this value, and you see that the fraction of the kinetic energy depending on the mass of two objects, and it defines the fraction of loss in the kinetic energy due to the collision is F equal to Ki is the initial kinetic energy minus the final kinetic energy divided by the kinetic energy initially, and this equal to this. Okay. Is there some message to me? Okay. Yeah. Nguyễn Huỳnh Đức. Okay. There are some question, Nguyễn Đức Long. If you type the message and I don't see it, you can speak out. Nguyễn Đức Long, you have some question?
No, I think it is the previous question that you answered me.
Okay, sorry, I'm sorry. I see the chart and then, okay, right, thank you. So we continue. So far, we consider the case in the collision in 2 dimensions. How about in 1 dimension? So how about the case in 2 dimensions? So in 2 dimensions, we do similarly, except we write the momentum conservation in the vector form, okay? And then you project one by one along a x, along a y, and get the equation. And also you need to get the angle, because it's not in one line anymore, but we for example, after collision, they're moving with a different direction, right? So then in this case, you need the vector expression. So this equation is still true, but you need to write in the vector form, and then you project along OX, along Y. You do similarly as you do with the force. And in case of elastic collision, you apply the kinetic energy conservation. And remember that in the kinetic energy, when you calculate the kinetic energy is 1/2 mv squared. So velocity here is the magnitude, not the direction anymore. So in the condition for the kinetic energy, that is a number, scalar quantity. It's not a vector. But in case of momentum conservation, here is a vector sum. And here is the number sum, that's a scalar quantity. Remember, okay? And give you the magnitude of the velocity. And here give you the vector velocity, not only magnitude, but also the direction. Be careful. We have example exercise to do to understand this. Okay, so this similarly. So we do this exercise, and then for one dimension is simple. So we just make 2 dimension in general case, so that we understand deeper this application. So please do this exercise and send me the results by chat box privately. Okay. Okay. Sorry, do you have any class after my class? Any other?
No, we don't.
No, we
Okay.
don't.
Okay. So I can wait you to do this exercise because I'm scared. There are someone is waiting for me, and remember you calculate the fraction of loss of the kinetic energy. So what is it? F equal to Ki Kf divided by K. It's called the fraction. Okay. Okay, Hoàng Bảo Nguyên. Yeah. You are allowed to get out. Yeah, no problem. I don't see there are many solutions. I call Nguyễn Trọng Nhân.
Yes, I'm here.
Can you present?
Okay.
Let me, one second. I want to write your name. Nguyễn Trọng Nhân, BI12 335, right?
Yes.
Okay. Please.
So with the A section, they ask the velocity after collisions. So I'm not 100% sure about my answer, but I just use the formula.
Okay, so let wait me 1 minute. I denote the name. I name it M1 here, and here is E1, and M2, U2.
Yeah, that's right.
After collision, they stick together, moving
yes.
with the velocity v. Create the angle theta here. Okay.
Yeah, I use like that, and I just use the formula.
Momentum conservation.
Yes, that's right. I just use like the mass of the A.
Yes.
A thingy plus with the multiply with the velocity use one
vector
plus
form
plus the mass of the B object multiply with the velocity of the velocity 2 and equal to the mass of the first one plus with the second one total multiply with the the V. Yeah. So
because they are moving with the same velocity after the collision.
Yeah, that's right.
Okay.
So we got like the first one like is do I need to tell all the step of the formula, or I just need to say the answer for the V?
Yes, you tell me how can you do this step by step.
Okay, so the first is we have the mass and the velocity of the first one, so it will be 120 kilogram per meter per second, and the second one will be 400. So we got 420 plus with 400, we got 820. And then we got the mass of two objects. We got like plus with each other, we got 120. So
M1 is 70 and M2 is 50. So sum of them is 120. Okay. So now you have vector form. How can you move to the magnitude?
to make. Sorry, can
So
you
this is a vector
ask
form.
again?
This is a vector form. How can you get the equation for the value, magnitude value?
Oh yeah, I forgot. Sorry, I do like the like it's like the Pythagoras formula. So I square each other. Sorry, I forgot that
Okay,
step.
so you need to draw the diagrams. So you have
Yes.
this vector. This vector is M1 U1.
Yeah,
Okay?
sorry, I forgot that step.
Okay, no problem. So this vector, this direction, right?
Yes.
Vector here is M2 U2. And then this vector is sum of these two vectors. So just obey this rule. You have sum of them is M1 plus M2V is a vector. And theta is this.
Yes.
angle.
Yes. Yeah, that's right.
And then because they are perpendicular to each other, so you apply Pythagoras for this triangle.
Yes.
Right?
Yeah. Yes.
And then you get this length. Square equal to this square plus this square. Is it true?
Yeah, that's right. Yeah.
Okay. So, okay, this guy is 120. So 120 V square. Sorry. 120 V is this length square equal to this 70.
It will be
U1.
420 square plus with the 400 square.
Yeah. U2 square. And also you plug U1 and U2 in, right?
Yes, that's
so
right.
This one equal to
420 square.
420 square.
The last guy is 400 square.
So it means that 20V equal to 420. Is it okay?
No, it's I still say the
sorry, plus.
Yeah.
Yeah.
400 square, 400 square.
400, sorry,
Yeah,
square. And from here you get out 120V equal to
let me take again. We got 580.
580.
And so we got V equal to 4.83
unit
meter per second.
Very good. Okay, good. And a velocity means, because velocity is a vector, so you need to estimate not only the magnitude, this is magnitude, but also the direction.
Yes.
Direction means it creates with the horizontal an angle theta. How about the theta?
So the theta, I use the tan.
Yeah, very good.
So we got like the
tan theta is this guy divided by this guy.
Yes.
M2 U2 M1 U1 50.
Yes. So the theta will be 43
400 divided by
400 divided by 420. So we got the theta will be 43.
Theta is
43.
43
Yeah.
degree.
Yeah, degree. Yeah.
Very good. Okay. So number B.
So with the number B, I just first I will calculate the total kinetic energy before the collision.
Very good. Okay.
So we got the
1/2,
formula.
right?
Yes. That's right.
Okay. Then you plug the number in.
Yeah, so so I just need to say the numbers, or
Yeah.
so the number for the kinetic energy before collision will be 2,860 joules.
Very good.
So
Final.
yeah,
After collision.
after collision.
1/2 m1 plus m2 v square, right?
Yes, and
Equal
that
to
will be total 140 joules.
100.
1,400 joules. I'm sorry.
Okay, right, like this.
Yes.
Very good. So the
So
fraction
yeah, so the
is
fraction loss will be the total kinetic energy.
very nice. Right?
Yes, and it will be 0.510
Okay. Yeah.
like that.
Yes. And then if you want to express by percent, you can multiply by 100%, and this one is 51%.
Yeah, 51%. Yeah.
So it means that there are already 51% of the kinetic energy convert into another form of energy. Okay?
Yeah.
Yeah, very good. Thank you very much. Trọng Nhân. Perfect. Do you, is it clear? Do you have any further question? Let me check the chat box. V1, V2. Many, many wrong answers. So is it clear now, everyone? Okay. So actually, you can do this way, or more general, you can do another way. Let me do it by another way using the projection or long OX and OY. For example, if they are not perpendicular to each other initially, for example, initially this guy moving like this, so they are not perpendicular. How can we do that, right? So in this case, of course, we know the angle. So in this case, how we do it? So I think more general case, we can do like this. So I do exactly the same as Trọng Nhân has done. That is M1, U1, M2, U2, right? So I apply the momentum conservation is M1, U1 plus M2, U2 equal to M1 plus M2, V. So now this is a vector form. So I can project one along OX. Okay? Project along OX, I have M1, E1 is along OX. So I have M1, E1. U2 is 0 because it's perpendicular to OX. Equal to M1 plus M2 Vx, right? This is Vx. And Vx equal to V multiplied by cosine theta. So equal to M1 plus M2 V cosine theta. I have second question. So now I project along OY. M1 E1 is 0 because it's perpendicular to OY. So only this guy. So M2 U2 equal to M1 plus M2 V Vy equal to V sine theta. Okay. So from 2 and 3, if I divide side by side, I get tangent theta is equal to m2 u2 divided by m1 u1. And exactly the same as Trọng Nhân has done, is 0.5. And then you can calculate alpha. Okay? So how about the magnitude velocity? If I square this both sides. So I get v cosine theta equal to m1 u1 divided by m1 plus m2. V sine theta equal to m2 u2 divided by m1 plus m2. If I square both sides, okay, so the left hand side is a v square cosine theta square plus sine square theta equal to the right hand side. Okay, so this one is 1. So then you can calculate v square is this. You plug the number in, and I believe that v will be equal to 4.83, right? The same, I believe you get the same answer. Okay? And for fraction, you do similarly. It's exactly the same as Trọng Nhân has done. But this way, I mean, if they are not perpendicular, you can use this. Project along a x, along a y. For example, initially this guy moving here with the angle 30 degrees, then you project, when you project, you get the information. Okay? This particular case, they are perpendicular. But in general case, you can do like this. Project along a x, you get one equation. Project along a y, you get another equations. And then you can solve down all the parameters you want to determine. Is it okay? Is it clear? Any question? Okay. Okay. So we finish the class now, and I make this announcement to you. We have one more class after the week, next week. Okay, in 2 weeks, right? So for the last class, we have 2 hours. And in these 2 hours, I'm planning for you to do a midterm test. So my planning for the midterm test is, as I explained in the beginning, that it takes about half an hour. And the question is multiple choice question, as I give you to do the example for the previous class.
Teacher,
Okay.
is in the Moodle. We do in the Moodle.
Let me think about it. Because I didn't prepare actually, because
Okay. Okay.
you know, this year you are quite you are too crowded, let's say, the first time, so it's very difficult for us to handle with many students at the same time. So I'm considering, and also the Moodle, I'm not be familiar with it. So let me check. I'm thinking about the Google form, which I use it many times, but Moodle I haven't ever tried, because with my question I don't have the word, but I have to write in the LaTeX, another language. I don't know if it works or not, but anyway, we have a multiple choice question. You do half an hour. So for the last class, I first give you the lectures. And then remaining times half an hour, I will give you the question to do the midterm test. And you remember that the midterm test will be calculate the fraction, the midterm. So the midterm will be equal to 70% of the multiple choice question. Okay?
Okay.
Plus 30% of what you have done during the tutor, the exercise. From the tutor, I get 1 mark from the tutor. I get a list. We get from the tutor 30% plus a multiple choice question, 70% if we get the midterm mark. Is it clear?
Yes.
Okay.
Okay.
And also the content of the midterm test, I will limit from beginning until the lecture today. Is it okay?
Yes, okay.
Yeah, and also I will post on Moodle my lecture slides for you to review.
Oh, thank you.
Okay.
We really want that for a long time.
Yes,
Thank you.
Thank you very much.
All right.
Okay. So, because finally I will provide you the slide lecture so that you can make a revision before the exam for you to well prepare for the exam. So I don't want to make any difficulty for you. Okay. And also I already take note all the people active students during my class. I will give you the bonus mark. I will decide later for the final mark. Okay. And we still meet one more times. Do you have any other ideas? Is it clear? Any more questions?
No questions, but I do have a question related to the classes. So next week we don't have classes with you, but the week after we have it, right?
Yes. So
Okay.
next week you have a tutor for what you have done. So next week you have tutor, and the week after we have the final class and also the midterm test.
All right.
All right.
Okay.
Okay. Thank you very much for your attendance. Bon weekend.
Goodbye, teacher.
Bye bye. See
Professor.
Bye, teacher.
Bye,
See you next
teacher. See you
time.
next
So,
time.
you next time.
later.
Yeah,
Bye, teacher.
see you next
Bye.
time.